Swayam Prabha. Digital India. Educated India.
This is our continuing series of lectures on diffusion dominated transport, and as I told you, we were looking at the case where we have to solve the diffusion equation, the Laplace equation for either the temperature or the concentration field is equal to 0. Okay. So, the equation is basically of the form k del square T plus any sources or sinks is equal to 0. Okay. We had considered a specialized kind of a source, which is a point source. Okay. That point source, it is located at a point, the volume of that goes to 0 in such a way that the energy generated per unit time is a constant. Okay. Okay, so, you have a point, a source whose volume goes to 0, and therefore, if the energy generated is a constant, the flux has to go to infinity. Okay. We had defined the delta function previously. Okay. In this particular case, the delta function is defined such that delta of x such that delta of x is non-zero only at x is equal to 0 and it is equal to 0 everywhere else. The integral of this delta function over the entire volume has to be equal to 1. So, it is an idealization of a function which is non-zero only in the at the origin, where x is between minus h by 2 and plus h by 2 and y is between minus h by 2 and plus h by 2 and z is between minus h by 2 and plus h by 2, and within this region it has an amplitude of 1 over h cubed. There are other ways of expressing the delta function as well. This is the simplest way. However, regardless of how you express the delta function, the solutions that I get for this delta function will end up being the same. So, I showed you that if we have an equation, of the form k del square T plus q delta of x is equal to 0, the solution of that is temperature is equal to q by 4 pi k r. So, this temperature field is the solution for the Laplace, or rather the Poisson equation, a Laplace equation with an inhomogeneous term. So, I had shown you that when the source is at the origin, you get q by 4 pi k r, where r is the distance from the origin. When the source is at some other location, you just have to take the distance of the observation point from the source point, the vector distance, that in this case was equal to the magnitude of the vector x minus xs, where x is the observation point and xs is the source point. I had shown you superposition. If you have two different sources at the observation point, you can find out the temperature due to each of those sources individually and add them up, and you will get the source the temperature due to the two sources together. That works only when the sources are in the form of delta functions, when you have point sources of infinitesimal volume. In general, if you have sources of finite volume, that principle does not apply in general. You have to keep the solid boundaries the same. So, therefore, this source of the delta function type is a special source, and that is the reason that it is useful for getting these equations. So, I showed you that for two sources you can get a solution by a superposition. Now, what if you had some volumetric source? You had some region in space, where let us say some reaction was generating a certain amount of heat. A reaction was generating a certain amount of heat. That heat being generated per unit volume, per unit time, I will consider as q of x prime. I should be careful here because I have used capital Q for an energy per unit time. So, rather than using that, I will use a different notation for the energy per unit volume per unit time. So, I will consider this as some source S of x, that is the energy generated per unit volume per unit time. And I want to find out what is the temperature at some observation point x. That observation point could be within the source or outside, it does not matter. So, how do I do that? I already have a solution for a point source. That solution is T is equal to Q by 4 pi k. Let me write this as a source point. So, that is the temperature field for this. So, what I can do is I can take this object, divide it into a large number of small volumes. The volumes can be defined with centers at delta V1, delta V2, etc., delta Vn, divided into a large number of volumes. I label them as 1, 2, 3, 4, 5, etc. The volumes are delta V1, delta V2, etc., up to delta Vn. The centers are at locations x1 vector, x2, xn. So, the sources within this volume are going to be of the form S at x1 delta V1, S at x2 delta V2, S at x3, and so on. So, those I can consider to be point sources at the centers of each of these volumes. These I can consider to be point sources at the centers of each of these volumes. If the volumes are small enough, the fact that you are combining the entire source at its center does not affect the problem, because the extent of the volume is much smaller than the distance from the observation point of each of these. The extent of the volume is much smaller than the distance from the observation point. So, this is effectively a point source. So, once I have defined it this way, I can straight away write down what is the total temperature field. I just have to add up the temperatures due to each one of these point sources. So, therefore, the total temperature field will be equal to summation over all I is equal to 1 to n of delta V I into S of x I. Let me use a capital index here. Times the source at the location xi divided by 4 pi k into x minus xi. So, I have just added the temperature due to each one of these point sources. The source strength in this case is delta V times the source, that divided by 4 pi k times the distance between the source point and the observation point. That is my expression for the total temperature. In the limit as delta V goes to 0, I can equivalently write this as an integral over the volume. This is integral over the source volume. This is integral over the source volume of the source strength at that location by 4 pi k into x minus x prime, okay, where x is the observation point, x here is the observation point, okay. X prime is the source point, okay. X prime is the location on the source, and you are integrating over x prime, which is over the entire volume of the source, okay. Okay. So, this one here is the source point, and this s is a function of the source point, and the integral is over the source point, and from that you get the value of the temperature at the observation point x. Okay. So, you can do that for any distributed source, okay, for any finite object, okay. Provided the source is specified, you can get the temperature field at any observation point by using, okay, this expression. Okay. So, this effectively, okay, so recall that we started off trying to solve the temperature, okay, k del square T plus S of x. Is equal to 0. That was the differential equation for the temperature that we were trying to solve, the Poisson equation with an inhomogeneous term. Okay. And using this delta function construction, we have managed to get a solution for that. T is equal to integral dv prime s of x prime by 4 pi k into x minus x prime. This is an integral relation. This gives us on the left side, this gives us the temperature at the observation point x, okay, the temperature at the observation point x as a function of the source location and the source strength, okay, distributed source. So, this is effectively the integral equation that corresponds to this differential equation. Okay. There is a solution of this differential equation, and you can use this formulation to find out the temperature due to any field. Okay. So, let us briefly look at how we would do it for a simple problem, okay, and that is the heat generation due to a wire. Okay. Okay. So, if I have a wire, okay, of total length L, okay, extending from y equals minus L by 2 to y equals L by 2. Okay. This is generating some heat. Okay. So, this is a finite wire. You can think of it something like an immersion wire, for example, okay, which is immersed in a fluid. It is generating a certain amount of heat, and you would like to find out what is the temperature field around this due to the presence of this wire. Okay. The heat being generated is equal to S per unit length of wire per unit time. Okay. That is the heat that is being generated. This wire is of infinitesimal thickness. Okay. So, it has 0 thickness in the x direction and 0 thickness in the z direction. Okay. And it is a certain amount of heat generated per unit length. Okay. So, we have to solve the equation k del square T, okay, plus, okay. This has infinitesimal thickness in the x and z directions. Okay. So, this is delta of x, delta of z, okay, times S, okay, okay, is equal to 0, okay, where S is non-zero only for y is equal to minus L by 2 to y equals plus L by 2. Okay. Okay. So, S is source per unit length of wire. Okay. It is confined only to the y axis. That means, it is non-zero only when x is equal to 0 and z is equal to 0. Okay. Otherwise, it is 0. Okay. So, it is non-zero only when both x and z are 0. Therefore, I have delta of x, a function that is non-zero only when x is 0, and delta of z, a function that is non-zero only when z is equal to 0. and I want to find out the temperature at some observation point x, y, z. Okay. So, therefore, I need the inverse of this equation, which I had told you T of x, y, z is equal to integral, okay, over the source point. Okay. That is integral dv prime that I had in the previous example. The source, okay, s times delta of x, delta of z, primes here. These are the source locations. Okay. Recall that in the previous class, in the previous lecture, I have k del square t plus s of x is equal to 0. The solution for that is integral over dv prime of s of x prime divided by 4 pi k into x minus x prime, okay. Okay, divided by 4 pi k into what is x minus x prime. Okay. This is going to be the distance between x and x prime. Okay. So, this square root of x minus x prime the whole square plus y minus y prime the whole square plus z minus z prime the whole square. Okay. So, that is the distance between the 2 points. That is what is meant by the magnitude of the vector x minus x prime. Okay. So, this will be x minus x prime the whole square whole taken the square root of. So, that is going to be the expression. So, x goes from minus infinity to infinity, y from minus L by 2 to L by 2, and z goes from minus infinity to infinity. Okay. So, that is the extent, that is the temperature field. Okay. Now, we know that integral minus infinity to infinity dx prime times delta of x prime times any function of x prime is equal to the value of that function at x prime equals 0. Okay. That was one of the properties of the delta function. It is 0 everywhere except where x is equal to 0. The integral is 1, and if you multiply it, this delta function, by any function, okay, some function f of x, okay, and you integrate it from minus infinity to infinity, the delta function is not 0 only at x is equal to 0. So, this will pick out the value of the function at x is equal to 0. Okay. So, that is one of the properties of the delta function. So, in this case, I have the integral over x, okay, of delta of x prime, okay, integral over x prime of delta of x prime times some function of x prime, okay, times some function of x prime. Okay. The result is going to be the value of that function at x prime is equal to 0. Okay. The value of that function at x prime is equal to 0, okay, which will be equal to minus L by 2 to L by 2 dy prime integral minus infinity to infinity dz prime s delta of z prime divided by 4 pi k times the value of the function at x prime is equal to 0, x square. Okay. The value of this function at x prime is equal to 0. Okay. Okay. And then I have the second integral over z prime of delta of z prime times this function of z prime. Once again, it will pick out the value of the function at z is equal to 0. Okay. So, this is the expression for the temperature, where I have to integrate over the y coordinate over the length of this wire. Okay. Over the y coordinate, I have to integrate this over the length of this wire. Okay. You can do this integral. I will not go into the details of how the integration is done, okay. But in the end what you will get is s times log of L by 2 plus y plus root of x square plus z square plus the whole square. Whole square. Now, this is a rather complicated expression. What we can do, for example, is to simplify it by taking the value at the location z is y is equal to 0 along the central plane. Okay. I will take the value of the temperature along the central plane, okay, at the location y is equal to 0. Okay, at the central plane where y is equal to 0. In that case, okay, the temperature becomes T of x 0 z is equal to s into log of L by 2 plus root of So, this is the temperature field. Okay. We do not get very much physical insight from this temperature field. We can get physical insight, however, if we consider two limiting cases. Okay. The first is where the distance, okay, from the source point, okay, that is this distance is of course square root of x square plus z square. Okay, that distance, you could consider limiting cases where that is large compared to the length of the wire L and where that is small compared to the length of the wire L. Okay. So, the temperature as I have written it for you is equal to 1 by 4 pi k. Okay, so, that is S by 4 pi k. I may have missed that S over here. I should have a 4 pi k here, okay, in both of this. Okay. That comes out of this 4 pi k over here, okay, okay, into log of L by 2 plus square root of the whole square okay. If we take the limit where the distance from the source x square plus z square is much larger than L square, the length of the wire. Okay. This distance is much larger than the length of the wire, and I have to do a series expansion in the small parameter L by 2. Okay. I have to expand this entire term in the series expansion in L by 2. I will get S by 4 pi k. Okay. I divide both the numerator and the denominator by x square plus z square, the square root of. Okay. So, I will get L by 2 root of x square plus z square, okay, plus root of 1 plus the whole square. And now I can do a series expansion because this L is much smaller than root of x square plus z square. So, these numbers are small parameters, okay, compared to 1. Okay. These numbers are small parameters compared to 1. And if you do that, okay, you can actually neglect this term because it is quadratic. Okay. I get 1 plus x by 1 minus x. Okay. The result of that just turns out to be equal to s by 4 by k, okay, into L by root of x square plus z square. Okay. That is what I would get by expanding out this log function in a binomial series. Okay. Recall now along the plane that we had in the xz plane, okay, along this xz plane, okay, where the wire was in the along the y axis. Okay. Along this plane we had done an expansion, okay, where the distance was root of x square plus z square. This was large compared to the extent of the wire L. Okay. That was the limit that we were considering. In that case, we get a solution which is basically equal to the total heat generated per unit time. Okay. S was the heat generated per unit length per unit time of the wire. So, S times L is the heat generated per unit time divided by 4 pi k into this x square minus z plus z square, which is basically the distance, okay, from I should write this as square root, my apologies, the square root of x square plus z square, which is basically the distance from the origin. Okay. That was the solution that we had got for the point source q by 4 pi k r. Okay. So, if the distance from the source point is much smaller, larger than the extent, okay, if this distance is much larger than this length, okay, the source point actually looks like a point source of source strength S times L. Okay. So, as the distance from the source becomes much larger than the spatial extent of the source, it basically looks like a point source. Okay. So, that is the idea here. Once the spatial extent is very large, you get back the same result that you would have got for the point source. Okay. You can consider the opposite limit. Okay. X square plus z square is much smaller than L square. Okay. That is, the distance from the source is much smaller. Okay. So, if I look at this in the xz plane, okay, the distance here, okay, x square plus z square root of is much smaller than the length of the wire. Okay. So, you are going only a small distance compared to the length of the wire. In that case, you have to take the opposite limit. Okay. In this expression, okay, x square plus z square is much smaller than L square, and I need to do an expansion in the case where, okay, for x square plus z square by L square much smaller than 1. Okay. I will not go through the details. Okay. You can work out the expansion. What you have to do is, rather than dividing throughout by x square plus L square here, x square plus z square here, I have to divide throughout by this L square. Okay. I have to divide throughout by this term. Okay. And if I do that, I will get the temperature is equal to q by 4 pi k log of L by root of, I am sorry, q by 2 pi k L by root of x square plus z square. Okay. Therefore, the temperature field goes as the logarithm of the distance. Okay. The temperature field goes as the logarithm of a distance. What happens when the distance is small compared to L? Okay. The wire effectively looks like a wire of infinite length, because the distance from the wire is much smaller than the length of the wire. So, the wire effectively looks like a wire of infinite length. The problem effectively reduces to a two-dimensional problem, okay, where in 2 dimensions, the x and z dimensions, you have a wire which is generating a certain amount of heat per unit length in the third direction. So, this is the equivalent of the delta function source, the point source in 2 dimensions. The point source in 2 dimensions has a solution which is logarithmic in the radius. Okay. You can solve explicitly the point source in 2 dimensions by taking the 2 dimensional version of the equation del square t, okay, plus q delta of x is equal to 0. In 2 dimensions, if it is axisymmetric, you get 1 over r d by dr of r partial t by partial r plus q delta of x is equal to 0. The solution set for this turns out to be a logarithmic function. Okay. You can solve that quite easily and verify that you will get a solution that is of this type. Okay. So, in the 2 limiting cases, we get the correct solutions for this case of a wire. And of course, this can be generalized. Okay. In this case, we took a 2-dimensional wire. You can take a surface or you can take a volumetric object. Okay. For all of these, you will get solutions just by inverting this equation. Okay. Just by taking the inverse of this equation. Okay. The inverse of this equation, okay, the differential equation is basically this integral equation. Okay. And we saw that by expressing it first as a point source and then generalizing it to a volumetric source. We will see a little bit more about this. What do you do? This was all in an infinite domain. What do you do when there are boundaries? Okay. We will look at that in the next lecture. Then come back to the original point that I had said. What do those spherical harmonic expansions mean? That we will continue in the next lecture. I will see you then.